Hello everyone, and welcome to our sixth workshop of the quarter, where we'll be covering two-pointers and optimization. So you can follow our slides with this link, good, and then our agenda for today, we'll start with a quick review of two-pointer algorithm, and as an aside, then we'll talk about optimization and algorithms efficiency, talk about caching, concurrency, and everything you want to know to do well in CS32, in CS33 and your technical interviews. Okay, so let's start with two-pointers. So essentially, when we say two-pointers, we call two different techniques by this name. First is when two-pointers start at different positions, and one starts at the beginning and while other start at the end. And the second technique is when they both start at the same position but move with a different speed. So to see what it actually means, let's take it one by one. So the first technique, usually you would use it on sorted arrays of any kinds, and you start at opposite ends. By the way, when I'm saying pointers, I rather mean indices in the array than actual pointers that you might have used to see in CS31 and 32. So those indices, while they're in order, we will increment the left one, or decrement the larger, the right one, and depending on if our condition is met or not. So to understand how this works, let's go through a first technique example. For example, let's say you're given a sorted array and you're trying to find out if there exist two elements of this array whose sum is equal to 4. Well, what you would do, you start with first left pointer at the beginning and right pointer at the end of the array. You check the sum of the elements. It's -10 plus 7, it's -3, less than the target sum. So what do? You move your larger pointer to the left to decrease. Excuse me. You move your left pointer to the right to increase the sum. So now you get this situation. Now the current sum is -1 plus 7 is, sorry, this is 6. This should be 6, which is now larger than our target sum. So instead, you would move your larger pointer to the left to decrease the sum. And finally, you get that the sum is -1 plus 5 is 4. So we conclude that we do have such two elements that their sum is 4. Notice that if you wanted to find all such pairs, we would simply continue our algorithm until x is still smaller than y. Okay, so with this in mind, let's go through a small practice problem. Now I see you might not see clearly. So essentially, you're given an integer array, and you want to find all triplets such that the triplets have different indices, and the sum of the elements in the triplet equals to 0. So we have this one example here with elements -1, 0, 1, 2, -1, -4, and the output is -1, -1, 2. Their sum equals to 0. So basically, this 3 elements and another triplet -1, 0, 1. We don't want our solution to contain duplicate triplets, so we only include these 2 triplets once, although we might find different elements that sum up to 0. Okay, so how would we solve it? Okay, first of all, do you know what the brute force solution would be? Yeah, exactly. We can just have 3 nested loops, but unfortunately, that's too slow. That would be all of uncubed time complexity, so we want something faster. So here we would use two pointers first technique. Well, first, remember that the first technique, it usually works on sorted arrays. So whenever you're given a sorted array and you're trying to find out some properties of its elements, maybe sum of 2, 3, 4 elements, that's a good indicator that you might want to use two pointers technique. So first, we'll sort the array. Now, as we have sorted array, we'll have an outer loop which will go over the first element of a triple. So we would have index I that will point to this would be our first element of the triple, and then we'll work solely with the right part of the array and find two such indices that will give us the sum of 0. So notice that when we have our first element, -1, for example, our target sum is 0, and at the same time, we want to find two such elements in this part of the array, such that their sum would be 1, so that the total sum would be 0. So this is exactly the problem that we had before. We need to find two elements in this part of the array with some certain sum. Only in this case, we need to find all such pairs. So our solution will change a little bit. So again, we start with I equals to 0. By the way, what would be the bounds for our outer loop? What would be the maximum value of I in our loop? Yes, exactly. So we have 3 elements in the triplet. So we know that the first element of the triplet would be at least, well, at most, at this position, 2 elements from the end. Okay, so with this in mind, let's start the algorithm. So we see that now the sum of our 2 elements is 6, which is greater than our target sum. So we move our larger index to the left, decrease the sum. Now sum is 4, still larger than the target sum. So we move one more to the left. Now our target sum is exactly 1. So we'll store this triplet into some data structure, array, vector or set or whatever we use in our actual implementation. And now notice that we can actually, it doesn't really matter which index we move, since if we move x to the left, we'll still get something larger than we already have. And if we move y to the left, then we will get something smaller than we already have. So we can actually move both of them towards each other. And again, surprisingly, we see that the sum is again 1, which is what we need. On the next iteration, our x and y will switch their positions, and that's an indicator that we should stop. So they came to each other, so we should stop our search. Okay, so that should be the end of the case when the first element is at the position I equals 0. Now we move on to the case when I equals 1 and basically repeat the algorithm. Okay, so, and we go until I equals n minus 2. All right. Well, with this in mind, there are some things that we should be careful about. Well, for example, in the task, we saw that there should not be any public duplicate triplets. Therefore, every time we encounter a triplet, we want to skip through duplicate elements so that we don't count them again. We'll see that in actual implementation. And also, we should always check that we're within the bounds of the array. So our first index goes towards n minus 2, and second and third indices always are in order. All right, so knowing this, let's look at actual, well, one possible implementation of this algorithm. So let's look at it step by step. First, as I said, we sort the array. Then, well, we decide to store our results in vector, in part because the solution template we were given requires us to return a vector. But there are always different variations of where you can store your result. So we declare vector, and then we'll notice that the problem is only valid if the size of the array is at least 3. So we ignore all other cases. And for cases when the size of the array is at least 3, we have our outer loop from 0 to n-2, as I said. And notice this part here. We skip the elements, the duplicate elements of I, the first elements of the triplet, since we don't want duplicate elements in our resultant vector. And here, this is where the 2-pointer part happens. We have our first pointer x, second pointer y, at the beginning and the end of the part of the array. And while the condition is valid, so while x is less than y, we would calculate our sum. If the sum is greater than 0, we would decrement the larger index. If the sum is less than 0, we would increment the smaller index. Otherwise, the sum equals to 0, so it means we found our triplet, we store it. And then again, we skip through same elements, skip through duplicate elements here and here. And finally, there's, up to the user what exactly we want to do here. Here, I just decrement the larger index, but we could do both or just increment the smaller index. Doesn't really matter. And we return an array. All right. So do you have any questions about this part? Good. So if there are no questions, let's move on to our second technique. So the second one, if you remember, we have 2 pointers that start at the same position and they move with different speed. So here, when we say pointers, we would actually mean pointers, let's say, to nodes of a linked list. So this technique is usually used in linked lists, and whenever you are asked to find an element in linked list or find element with some property or calculate something with regards of elements of linked lists, you should think maybe you need to use 2 pointers algorithm. So to see how this works, let's look at this example. So for example, we're given a linked list, essentially the head of the linked list, and we want to find the middle element with only just one traversal. So notice how this says one traversal. Can you come up with any possible solution that uses more than one traversal and does not use anything we talked about before, any 2-pointer algorithms? Right. So you could go through all the nodes, find how many nodes there are, and then start over and go only to the, so you know the number of nodes, and then you go to node number n/2. Well, however, as I said, we want to do this with just one traversal. So what do? Well, we have 2 pointers that start at the same position here, and then one pointer will move with twice speed. What I mean by twice speed? When we move our one pointer, this pointer here to the next element, the second pointer, or actually I should make it a different color. We would move this pointer 2 nodes ahead. Then again, when I move the first pointer 1 to the right, the second pointer would move 2 nodes to the right. What this means is that basically when the second pointer reaches the very last element of the linked list, the first pointer would point to the middle element. And here we don't worry if the number is even because you're given that the number of elements is odd. But it will also work if you're trying to, come up with something, for linked list with even numbers of elements. So let's look at some pseudocode of this algorithm. Notice how in my explanation I didn't really include these statements, these if statements, if we are not, out of the boundaries of. Oh, excuse me. I turned it off. So notice how we didn't really care about the, if the next pointer is null pointer, if you're at the end or not. But this is something you always want to. This is always something you want to be careful about when writing actual algorithm. So as I said, we start with 2 pointers at the same position here with X and Y. And then while the second pointer do not point to the pointer right beyond the ends of the linked list, we check, we set our X to the next pointer, next node, and then we move our second pointer to next of next, well, 2 nodes ahead. Finally, we return our first pointer. All right. Do you have any questions about this part? Good. Then I'll hand it over to Neil. Some discussion on optimization.
All right, so first of all, let's start with some motivation on why we want to talk about this, right? We've already talked about a lot of algorithms, and we've always given the algorithms as time complexity for like their degree of efficiency. But sometimes you have to think at a little bit of a deeper level to see some of the insights about what we could do to make an algorithm better, right? So first of all, it's like a lot of industrial jobs, like if you're going to find internships, they're going to be looking for you to write like very good code in terms of performance, not just in terms of like algorithm efficiency, right? So there can be some situations where we have a very good time complexity for algorithm, but that doesn't always translate into being the best algorithm for the job, right? And as an example, do you have any ideas of like a situation in which an O of n squared algorithm can be faster than an O of n algorithm? Yeah, exactly. So what happens with time complexity is it often hides a lot of constant factors, right? So this O of n squared could actually be something like O of like 3n squared. But if we have an algorithm that's something like O of like 500n, because you have to do a lot of like constant processing before we actually get to the loop. If you have a small n, like say n is less than like 500, suddenly we have a lot better performance in the n squared algorithm than we do in the n algorithm, right? So it's not always a 1-to-1 ratio of what's going to be the best tool for the job, right? And here's a little example of how this works. So if you recall the lecture on dynamic programming, we gave 2 different examples of dynamic programming implementations of the Fibonacci sequence, right? So one of them is being done in a recursive manner, and one of them is being done in an iterative manner. So do you recall what the time complexities are for both of these algorithms? Okay, so that's half right. So the iterative one is just O of n because it's one loop, right? But I think you're thinking of the pure recursive solution, right? The pure recursive solution is to the power of n because it's doing the subcalls in like the form of a tree that keeps expanding, right? But remember what we did with dynamic programming is we were able to cut off all of the subcalls that we don't actually need to do, right? So even though it's recursive, it's still algorithmically O of n because we only have like one path that we have to go through, and that path is the depth of the tree is the same as this x that we're using, right? So they have the same time complexity, but we see that tabulation, which is the iterative version of TP, that's a lot faster. But the question is, why is this, right? We're doing the same exact algorithm in both ways. We're just calculating the Fibonacci sequence, but one of them's way faster than the other one. So again, this isn't something that you can just do while looking at the face of the problem, because at the face of the problem, everything's O(n). But if we look a little bit deeper, there's some like obvious similarities between the algorithm. It's both of them have the same amount of memory read and write, right? You see that when we are actually looking at these remember arrays, we all write the exact same amount, right? We're always going to be writing the values from 0 to x, right? And reading the previous two values for each one, right? So we're gonna have the same amount of read writes. And we're also gonna have the same arithmetic operations, right? All we're doing is having the previous values. So it's like f of 1 plus f of 2 is equal to f of 3. Right. So that's the same. So now what's the main difference? It's like one really like glaring thing that's different between them. Right. And that is one of them achieves all of this work through function calls. The other one achieves all of this work through loops. And what we're going to see here is there's a fundamental difference between using a function call and using a loop in terms of the overhead that it costs to do the same amount of work, right? So first of all, we can talk about what exactly is the overhead of a loop, right? So if we think about it in assembly, we're going to have something that looks kind of like this pseudo assembly code. Does this all make sense to you? Is it clear like what each one of these lines is doing? Okay, so sort of, let's try to make it completely clear. So first of all, a loop is implemented by a branch and a jump, right? Because we always want to check some condition, right? So, and the condition here, right, is going to be if whatever's stored in register T1 is greater than or equal to whatever is stored in T2, right, we're going to jump to the end. Right, so if you just draw the line, it's going to be a jump all the way here, and then we're going to keep doing whatever is left to do in the program. Right now, this ... this can be whatever you want it to do. Right, this is where the actual work happens inside the loop. So anything that you're trying to compute, any results that you're trying to take, this is all achieved in this ... which can be like anything. And then generally you have something like an increment here, right? So suppose that we have something in the T1 register. We're gonna just add 1 to itself, right? Because we're taking T1 and then placing T1 plus 1 into it, right? And then at the end of the loop, we're gonna jump all the way back to the start, right? We increment the counter, we jump all the way back to the start, and then again, we check the condition. And if the condition is true, we go all the way to the end, right? So this is a loop. Right, and remember here, we're defining overhead as anything where we're not doing work. So what is the overhead, essentially? Right, the jumps, the increment of the counter, and this branch. Okay, and that's pretty much the main part of it. And the key takeaway of this is when you have a loop, the main sources of the overhead are any register operations, right, which are pretty quick, as you've already discussed, and a branch, which could be pretty hard because you have to just check a branch, and there's a whole lot of complexity that goes into that you'll learn about later, right? But now there's a difference, like what happens when we call a function? So thinking back to when you were talking about like function calls in CS33, do you remember a lot of the stuff that you have to do to ensure correctness between functions? Yeah. Like the return address and then allocating the stack, everything. Yeah, that's pretty good. It's pretty good. So yeah, some of the things that I would just like pointed out here is obviously set up the stack, just like you've said. We can add over here, set up frame pointer. Like you're saying, set up the return address. Right. These are all fairly simple because you're just doing register operations. You're just doing register to register. And the critical thing is we also have like this register saving and argument passing. And these will involve moving things or storing things onto the stack. So do you remember exactly what the register saving is when you're moving between functions?
sometimes like services have to take their own values so that we might get.
Exactly. Yeah. So that's pretty much the gist of it. The whole problem is we have a finite amount of registers on our hardware, right? So the functions are going to be reusing them. And we want to make sure that whatever like values we have in the registers before are preserved until after the function call, because what if we need to use them afterwards, right? So that goes into the whole dichotomy of like which one's callee saved, which one's caller saved. But the more important thing is every time we save a register, that's a stack operation. We suddenly have to load something into memory from a register, right? And that's expensive. So as a combination of all of this stuff, as a combination of all of this stuff, we have a lot more to do when we call a function. And that really shows you it's like what the problem is between the iterative version of the Fibonacci sequence and the recursive version of the Fibonacci sequence, right? Even though we're doing the same amount of operations, like the O of n operations that we have to do, each operation is going to be a lot more expensive when we're calling the function because we just have to do more stuff. Okay? That's sort of the thing you should be thinking of when we're looking at an optimization. There's a finite bound on like how well you can do it in an algorithm, and then you have to make sure, okay, is this algorithm written in the best way that I can? Or if there's a better way to do it, you want to switch to the one that has the least overhead. Okay, so now that we've talked about that a little bit, we get into another just very important topic to be aware of, and that's how am I using the cache in all my stuff, right? And as a motivating example for this, this is a graph of the cost in memory strided summation. So what this is essentially doing is, we see this for loop here, right? This is translated from Fortran code, but we have some starting point, and we're going to be adding the same amount of elements every single time, right? But those elements are going to be strided. So when we're doing a stride length of 1, those are just going to be 4 million consecutive values. If we're doing a stride length of 8, we're going to be doing like, was that like 32 million size array, but then we're going to be only taking each 8th element of it. And what we can see is the time it takes to do all of these summations increases as we increase the stride, right? And the question is, why? Right? Why does striding matter in memory? Do you have any suggestions? Yeah, I kind of gave it away a little bit with the slide change, but yeah, it's all about cache misses, right? So if you think about what a cache is trying to achieve, right? It's trying to achieve two things. It's trying to achieve temporal locality and spatial locality. So do you remember what these two are? Yeah, exactly. So the assumption that you're making whenever you're using this caching system is you're saying, oh, if I request a piece of data from DRAM, I'm going to be using it a lot, right? Or I'm going to be using stuff that's near it, right? So what happens? We tend to pull in a large amount of stuff with each one, right? The cache block. So when we think back to what are we actually doing in this whole section, all we're doing is we're pulling in data one by one. And the only difference is the separation between all the data points. So just as an example, let's consider a cache that just contains 4 elements in this block size, right? It's a really simplified example, of course, like where you're generally not going to have just one cache line, and generally the block size can be bigger, but just for the sake of example, let's see what happens when we do a stride length of 1, right? So when we do a stride length of 1, we're going to be making our first access at point 0, right? And obviously we're not going to have that in the cache because we just started. So we have to pull in the entire block. So what are we going to pull in? We're going to pull in 0, 1, 2, 3. And something you notice is since we have a stride length of 1, we're actually going to hit every single one of these on the way forward, right? So when we pull in data into the cache, we're actually going to be using it 3 more times before we have to pull in something else, right? Now think about what happens when we have a stride of 2, right? since we start at 0, the access is going to be the same. So we're going to pull in the same data into the cache. But what happens now is we only use 0 and 2 before we have to pull in a different line. So now, instead of having only one cache miss per access that we have to do, we're now having 2, right? So we're like essentially doubling the amount of stuff that we have to actually pull in from DRAM. Right? Does that make sense? Yeah, and as this goes bigger and bigger and bigger, like suppose we have something like 4, a stride length of 4. What's going to happen is we're just not going to use anything else in the cache. We're just going to pull in the cache once. The next one's also going to miss, and we have to pull in another cache block, and we just have to do that over and over again, which means we're getting no benefit from the cache. It's as if we're just using main memory directly, and that's a lot slower. Right, so that's something that you want to be aware of when writing your code, because if you do something that's very poor in terms of cache locality, you're going to see a lot of slowdown that's sort of hidden, right? This isn't going to be immediately apparent when you're looking at code, right? And a great example of how this affects your code is strided memory access in terms of a loop ordering, right? So I think this should be very similar to what you've done in class already. But the setup over here is, suppose we have an array, right? And that array is a 2x4x8 array. And that's going to be represented in this memory block visualization here on the slide, right? Where I is going to be representing the first dimension, j is going to be representing the second dimension, k is going to be representing the third dimension. And the whole question is, which of these loop schedules has the least amount of cache misses, given that we have just one line of size 8, just to simplify things. Right. Do you have an idea of how you would go about doing this problem? Yeah. Mhm. Exactly. Yeah. So that's a great start, but how do you know that that's better than this one, where you go j and then I and k? Yeah, you are jumping around. So let's just take like a step back and just visualize this, right? And that way maybe it's more clear exactly why these two, which both have k as the first dimension that we're iterating over, one of them is better than the other, right? Naturally, you see this new, oh, IJK is fastest, but the professor will be very sneaky in your midterms. He'll like make the dimensions go different and make each value be something different. So it's always good to know how to do this, right? So first of all, right, what's a very nice thing about our cache? Very nice thing about our cache is exactly the same size as k. So we can just think of these as like big blocks of data that we're pulling in, and each block is just one row of k, right? So in this IJK order, right, maybe it's a little helpful to visualize exactly where everything is in this block, right? So as you probably already know, a 3D array is not represented in 3D in hardware, it's just one line, right? One line of memory. So how it's going to work is we have a 0, 0, 0 on this top left corner, right? And then over here, we're going to go to 0, 0, 1, because when we stride through this memory, it's going to be k first, right? Now moving all the way, 1, 2, 3, 4, 5, 6, 7, 8. In the middle over here, we're incrementing one of our j's, right? Because it's the next span in our data. Okay, so since each one of these lines has 16, we're actually going to see over here, we have 0, 2, 0. Then down here, we have our first I switch, where it goes 1, 0, 0. And then here we have 1, 2, 0. So that's how the data is laid out in this diagram. So when we want to do something IJK, what's going to be the direction of traversal here? We're just going to go through this block in a line like this. So sort of like we're accessing in a row major order. Why is this good? As you said before, we're going to find one miss, but then everything else in the block is going to hit, right? Because every single time we take a block, it's going to take this section. And that whole section that you're pulling in the block is exactly what you're going to access next. So we're getting really good cache locality here with this schedule. Okay. And the way this works is the next one's going to be here. Next one's going to be here. Next one's going to be here. So as we go through, we just keep getting the next contiguous block. And we're having really good access, exactly as if we were just striding through everything with the stride of 1, right? And as you saw in the graph, that's the lowest level of latency. So now the question is, what's going on with JIK, right? So let's just start with the first one, right? The first one is going to be this line through to here. But what happens here? Where do we go next? Two rows under here? Exactly. Yeah, that's correct. So I'll just do that in like black or something. The next place we go is down here. Okay. And then the place that we go after, we're going to increment J next. So we're going to go to this side and then to this side, and then just keep moving on from there, right? Now, in this case, what's our cache size? Our cache size is 8, which is the exact same as the amount of K values we have. So in this case, we're actually getting the same amount of cache locality as that first schedule, right? Because we take in one section that's going to be exactly one block. And when we make the switch to the next I over here, we're getting the next block, and that block is going to have everything hit again after the initial miss, right? So you are right in assuming that IJK is better than GIK. But now what's the reason, right? We're seeing that with the cache of this size, it's the same amount of hits. So where's the problem lying? Like, do you sort of have an idea of like where the problem could come from? We change like maybe a parameter, what we're given. Okay, yeah, that's fine. So what I was getting at is here specifically, we know that we have a cache of size 8, right? And that's perfectly aligned to our K values because there's 8 of them. But now what if we had 16 instead, right? What's our cache block going to be? Our cache block is going to be this entire row, right? So in the IJK schedule, we have one miss over here, but then the next 15, they're all hits, right? When we have the JIK, we're going to get halfway through this cache block and then jump over here, which is going to cause a miss, right? So do you see that this change in stride over here, that is a problem when we increase the size of the cache, right? And again, that's not immediately clear when you just go through the example. So it's always good to think intuitively, I want to just be striding through memory continuously. I don't want to be jumping anywhere. And that's exactly what you said the first time. It's because it jumps, right? And now just as an exercise, what is the problem with KJI, right? You should intuitively think, gee, this is the opposite of what I want to do. Now, the reason for this is we start over here in the 0, 0, 0 section, then we immediately jump in I, so we're going down like here, right? And then we move our J, so we're going to go like here. Whoop. Sorry, we're going to go like here somewhere. And then we're going to move in I. So this is like almost completely random access. And you don't want to do random access because every single time you're going to miss on the cache. So does that example make sense? It's like very good to think about, especially when you're just like sort of new at, you know, analyzing like what's going on in the cache. That will be given to you generally, right? And if it's not given to you, then you just want to look for whichever order gives you the best contiguousness, right? Because if this cache size is something really weird, like 31 or something, it wouldn't matter like in the terms of which schedule is the best. You always want to hit the one that gives you the most contiguous access. Oh, on your machine, that's data sheets generally. So yeah, I don't really have much experience with like checking out the cores. I think, wait, Suas, Ilya, you guys are in 35L, right? Doesn't he have one where you have to look up your device statistics
What?
for 35L?
Device statistics?
Yeah, like what core you're running on
Not
in
yet.
CSNet.
I imagine he might, if he does that, he will do it later on. They're currently unchanged.
Got it. Okay. So yeah, there's a shell command that I can't think of on the top of my head. I can like Google it during the break, but yeah, you can look up all of these statistics. If you have a GPU, then those GPU, the statistics are like widely accessible also just like on the internet and through like running a device query. And yeah, all the information will be there. Does that answer your question sufficiently? Okay, yeah. So next thing we're going to do is sort of give a motivation of caching. Before we do that, let's have like a quick 5-minute break. Or if there's anything else you want me to go over in like sort of this whole assembly caching sort of sense, then yeah, feel free to ask. Just pause the recording. All right, so moving on to an unresolved issue that we really haven't talked about, right? So first of all, are you familiar with that image, the memory hierarchy image? Have you seen that before? All right, cool. So you can see it is what we really want to highlight here is just the vast amount of time it takes to access memory, right? So when you're in a register, right, it's just going to take 1 cycle to access, and that's like acceptable because generally the goal of all of our processors are trying to do like 1 instruction per cycle, right? We can go slower than that if we run into delays. We can go faster than that if we start doing like instruction level parallelism. But it's like generally the goal is we're trying to do stuff fast. Right now, this is very not fast when you're accessing memory. So that's like a big problem. Right? We're going to take tens of cycles to access just the cache. Remember, these caches are supposed to be the fast way to access memory. So that's like all of that time that we're spending on accessing memory, that's instructions we can't do. Right? Because if we're assuming that we have a single program just only running 1 at a time, what's going to happen is we're going to be like chugging along, chugging along, chugging along, chugging along. And then we stop because there's like memory that we have to access. And then chugging along, chugging along, chugging along, right? Especially if we have a cache miss, right? If we have a cache miss, it's only DRAM is 100 cycles to access, right? That's terrible. And then even worse, if we have a page fault, and now it's going to take 100 million cycles to access the disk, right? That's crazy amounts. Like even though, to put it into perspective, like if you have like a computer running at like 3 gigahertz, right? 1 cycle is like in the order of nanoseconds. 1 disk access in the order of seconds. So it's just like, maybe that helps just like put into perspective how much we want to avoid doing that. And again, like you were talking about, that's part of the reason we implement like the page tables and translation look aside buffer, but that's like a little too tangential. But the problem is we can't really mitigate that, right? So we tried to mitigate the access times to DRAM by going to cache. But the problem is we can't always just rely on the cache, and even then the cache is pretty slow. So what happens? Are we just going to keep paying a penalty of just not being able to do anything? Right, and this is where concurrency comes in. All right. The main idea is when a task is waiting for something, just do something else. Like it's a very simple idea, but really hard to put into practice. And that image that I was showing you before, where it's just like we have some task running, and then we just have that break where we can't be doing anything. What if we just had another task to fill in that gap? Right? If you have something that's waiting for a disk read, then just execute something else that's not waiting on disk read until the disk read's done. So yeah, and that's the philosophy for a lot of operating systems. And the way that this is all implemented is through processes, right? And this is sort of the best way to say it without getting into too like technical of a detail is this is a running instance of a program, right? So each process stems from a program that you're running. You can think of it, it's like, oh yeah, if I open like Google Chrome, I open Firefox, there's like 2 different like code blocks that I'm running, they're both processes. And as processes, they get its own registers and they get its own virtual address space, right? And do you remember why we have virtual address spaces? Do you remember like some of the reasons for that?
doesn't have to worry about if there's another space and how it's going to.
Exactly, yeah. So it's sort of this isolation between processes, right? We don't want the compiler to have to worry about, say, like, oh, I want to place memory in location 128, but something else wants to put it there too. So now what do I do, right? So each time we give like a new virtual address space, we're essentially saying, here is your own full memory, right? And now you can do whatever you want with it. Right? So we have this natural sort of isolation between processes, and that can only be mitigated by talking to each other with dedicated like interprocedural communication. Okay, so the main sort of like takeaway from this is the way we support concurrency is by the operating system scheduling these processes, right? So what the operating system will do is when you have a program and it's waiting to do something like read from disk or like read from memory, it'll say, all right, you're done. I'll pull you out and then put something else into the processor to run, right? And now remember, this doesn't have to have multiple processors to do, right? You can do this all on one single core, which gives an illusion of multiple things running at the same time, right? So something like your computer, like imagine if your computer didn't have multiple cores, it could still do what it's doing right now, which is like running Zoom and like probably running Facebook in the background, doing like fetches to see if like you have any more text messages or anything. All that can be done on one processor, but just by interleaving the threads. Okay. So moving on, sort of the basis of what we want to do in concurrent programming is we want to be able to interrupt tasks whenever we want them, right? And this is basically like, if you don't have a task that's interruptible, you can't really like put anything else in. So if you just like, you're trying to do this schedule where you sort of weave two things in, but this task says, oh no, you can't interrupt me, this task will never run, right? And that's bad for concurrency. So you need the ability to perform fast and lightweight context switches. So are you familiar with what a context switch is? Not really, okay. So basically, you saw it before, right? Each processor or each process has its own resources, right? So what happens when we want to switch to a different processor, right? The whole, or to the different process, sorry. The whole point of having two different processes running is when we come back, right? It's as if it never stopped, right? We're not trying to restart the program every time we like stop and start it. We want to stop it, say, okay, you're at this point, and this is the point where we're going to keep going afterwards, right? So it's sort of similar to a function in that when you call another function for a function, you can't just get rid of everything the function's done already. You have to save something, right? So what are some examples of things we want to save in order to keep the state of the processor the exact same as it is before it got interrupted? Do you have any ideas? Registers, exactly. You have to save the registers. Anything else? Sorry, I can't. Yeah, what it has in memory, so it needs some sort of like heap pointer or something, right? And then maybe something else that it needs to save is the program counter, so it knows exactly where it needs to restart from, right? And without going too much in depth into what is all this, there's something called a process control block, right? And that's what you need to save, right? And all the information is sort of in there. So what a context switch is, yeah. From the IP? Oh, sorry. Yeah, that's the same thing. That is an x86 versus MIPS different, I think. Yeah. So yeah, the RIP, the instruction pointer saves like which instruction you're at. That's what the program counter is telling you. It's like telling you exactly the position of where you're going. Yeah, sorry about that. I'll choose that. What is it? RIP. Yep. So essentially, you have this sort of program state that's stored in the process control block, and you need to switch that in and out when you're switching processes, right? So every time you change to a different process, you need to save everything that you have to do on the first process, load in everything you have to do for the second process, and then start the one, right? And that overhead is called a context switch. Right. Now, the reason we want to perform fast and lightweight context switches for concurrent programming is the more overhead or the more time we spend on doing a context switch, that's the less amount of work that we can do in any given thing, right? So the CPU decides like where to schedule all of this stuff. And if the CPU is using some sort of scheduling system where like each process gets the same amount of time, imagine if it takes really long to do a context switch, we're suddenly getting like really small amounts of work done at every point in time, right? So we want it to be fast and we want it to be lightweight. We want to save a lot of things and we want less amount of overhead, right? The third thing is we need communication, right? One of the main things that we want to do with this concurrent programming system is we want to like launch a bunch of processes that all do like sort of similar things, and they all need to like sort of communicate to each other and like, okay, I've done this, I've done this, I've done this, right? So we need some sort of like inherent form of communication, right? We don't particularly like need this because, as I said before, there's like various ways of inter-process communication, like saying, oh yeah, we're going to reserve some shared memory so both processes can see that point in memory, or by doing something like message passing where we like actually send like messages between the processes to say, oh, I've done this, right? But we'll talk about that more in like the next lecture on like parallel programming. Yeah, but to support all of this, we have a concept of something called a thread, right? And now, the main important thing about a thread is it's just like a process in that it has a parent process and you sort of like spawn the threads, right? And they're each sort of doing something. They have their own like program counter and like, they have their own like registers and everything, right? But the main difference is they share their resources with the parent process, right? So the heap is the same between all the threads launched from the process. So you get that natural amount of communication by just saying, oh, we'll just write everything to like the shared memory, right? We also have interruptability because we do the same thing. We save the registers, we save the stack state, we save the program counter and everything, but we have to save less stuff than a full process. And that's like the main difference is it provides really fast context switches compared to processes, right? And this essentially allows us to hide the latency of accesses, right? So suppose you have a program that's going to be waiting for like 100 cycles for DRAM, right? What we can actually do is we can split this up into multiple like points of execution. And suppose this thing is waiting for the DRAM. Now we're going to do something else, right? And then over here, when this starts waiting, we can do something else. And now we sort of interleave the threads and we can hide the latency of the accesses, right? Because even though we're still waiting for that whole amount of time, something else is running. So we don't really worry about it. We don't have to count it, right? So is that all good? Right, listen, I just want to take like a step back. It's like, does everything make sense there? Okay. And again, if there's anything you want me to review, just like tell me for that, because like from this point on, it's gonna be like pretty advanced stuff, and you should just take it at like whatever pace you want to take it. Okay, so there's no such thing as free lunch, right? We got this really cool construct of concurrency where we can do a bunch of things at the same time, right? That's all cool and all, but there's got to be some issues that come from it, right? And without spoiling any of these issues, I can say debugging concurrent programming is very hard, right? Even like debugging like parallel programs is super hard, and there's a reason for all that. So do you think of any sort of issues that would arise with this whole idea of a CPU can schedule anything and interrupt anything? So think about it this way, right? Suppose you have a thread that's doing some sort of code, right? I'm just gonna pretend these are all code lines, right? And now this whole section of the code is doing something really important, right? Now suppose you want to do it twice as fast, so I just launch two threads. They're doing the same things. Maybe each one of them is doing a subset of something, right? What happens when the kernel decides to interrupt it like here at the very end? Is there any problems here? If we just do the whole first thread first and then do the whole second thread, right? They're gonna be any problems there?
Sorry, could you repeat that?
Oh, yeah. So suppose we just have two like code blocks doing something, right? And they're both like there's two threads running. They're all doing the same thing. Is there any sort of issues you can think of when we just run everything serially? In this case, just like everything in thread one, then everything in thread two, just like in a row. But I can sort of give you the answer. It's you're not going to expect to run into any problems, right? Because it already worked in serial. So it should work when we parallelize it, but then run it in serial anyway. Right? Does that make sense? If we just run everything at once and then everything on the other side at once, that's pretty much the same thing as doing it all just on one thread. Right? But now we get into some issues if, let's say, the compiler just decides to stop it there, or sorry, the kernel decides to stop it there, right? Now, maybe here, there's some sort of state that it didn't want this to see. And now there could be some problems arising with the fact that this thread is doing actions on something that the first thread never meant for it to see, right? And we'll get into an example of what could happen here, right? And these are really common example. You might have seen this in class. But suppose we're given an array, like 1,000 data points, and just to keep things simple, every single data point is just one. We want to take the sum of this, right? So what we're going to do, we want to make this fast as possible. So we're going to launch 10 threads that perform the summation of 100 numbers each. Okay. And now, remember, the threads all share the same program. So let's just suppose that what they're running is this for loop. Okay. As a very simple for loop, we're just going to have a start point. We're going to go from that start point plus 100. So we're just going to like subdivide it into 10 sections, do all those sections in one for loop. And this sum, remember, threads don't share registers, but they do share memory. So if we just store sum in memory as some sort of pointer, all the threads will be able to access it at the same location. Okay. So does what this code is doing make sense? So just summing up everything, putting it into sum. Cool. What do you expect the final sum to be? Right. So we know there's 1,000 data points, and all those data points are equal to 1. So what do you think is going to happen here? What's going to be the sum? Exactly. Do you have any intuition on like what are some issues here?
It's kind of like the other ones. The one up there.
Yeah. So almost perfect, right? Just one clarifying thing, right? We're assuming this is all done on one core when we launch these threads, right? So nothing can be physically accessing the sum at the same time, but there's something very similar that can happen when the kernel interrupts something in the middle of what it's doing, right? So let's think about it this way, right? So a possible generated code for the section of the pointer to sum plus equals data at I, right? It could be something like this, right? We have load sum into T1, which is just some register, increment that register, and then store it back. Cool. So again, as we talked about, if the kernel interrupts it here, right, in between the iterations, that's perfectly fine. We don't care, right? We've loaded, incremented, stored, and then the next thread can do whatever it wants. We're happy, right? But what happens when we do this? Right? We load the sum, we increment the sum, and then before we can store it, the kernel says, okay, your time's over. We're going to give it to something else. What's the problem? Right? You mentioned it already. It never got to write this value, right? So what's going to happen? Something like, let's say that thread 1 is at 49, thread 2 is at 149, right? What we could do is we could load in the sum that's at 49 here, increment it by 1 to 50, but before sum changes, we just go over here, and when this loads, we get 49, right? We don't get 50. So we add this to 50, store it in 50, and when we get back to this value, 50 goes in again, right? Now we just lost one of the rights, right? And this is called a data race, right? And a data race arises whenever you have some sort of shared data that's being read in that has like different behavior based on like the order of which threads get it first, right? And that's why it's sort of called a race, because it's like, oh yeah, all the threads are racing to get to the data and see who's actually like whose data update matters, right? There's a bunch of there's a bunch of patterns that you'll see. It's like read, modify, write, read, modify, read. It's like there's a lot of like different things, but you'll see that later in different coursework, right? Now the question is, what can we actually do to solve this, right? Now, are you familiar with what an atomic operation is? Yeah, so that's like one step further than this. So yeah, a lock, what it would essentially do is it would stop access to a resource until the lock is given up, right? This does things in a very similar manner, but essentially what an atomic operation is like, think about an atom, right? Until like very recently, people thought it was like the indivisible structure matter, right? And that's the whole concept. It's an indivisible instruction, right? So when you do like an atomic block, something in here can never be interrupted in the middle, unless the CPU actually wants to do it, and then I'll just do it anyway. But yeah, the sort of theory is that the CPU can never preempt the instructions or preempt the thread while it's in the atomic block. Sometimes they do it based on like a lock and saying that it's like, oh, until this thread comes back and relinquishes the lock, nothing can happen. But the concept you want to know is when you call something with an atomic instruction, that atomic instruction is always going to be done as if it's one instruction, even if it's like really long, right? So generally the theory behind atomic operations is you have to make them small so that you don't pay a lot of penalties for like just sort of keeping everyone waiting for a really long time if you're doing a lot of actions, right? So what you could do is, instead of having that whole like pointer, like addition and increment and everything, you just replace it with some sort of atomic load and increment operation. And this is like the syntax for this is different in a lot of languages. Like C++ has a standard template library for an atomic structure. And if you just increment the atomic structure, it'll just do that automatically. Java has some sort of like atomic type that you can just do call like a dot like load and increment, or like a dot like increment and get or something, right? And yeah, so essentially it ensures that no other thread can use the value until the atomic operation is finished, which is exactly what we want here. We want it such that the sum only gets updated fully by one thread at once, right? Essentially what that does is this just makes it serial, which is, you know, kind of countering like against the point of what we were trying to do, but it ensures accuracy, and accuracy is the one thing you never want to forgo when writing concurrent code. So, right, what is something else we can do? Well, we know that threads don't share registers, right? So what if we just took each sum, put it into a register, and then just serially added it later, okay? And that is sort of the idea that you will be doing in the parallel, or you've already done in the parallel, where you sort of want to split things up into parallelizable chunks, or in this case, like chunks that can happen concurrently, and then a serial critical section at the bottom. So what exactly is a critical section? We'll be talking about that next time. But sort of this is an idea to just prime like your brain into thinking, okay, how do we find parallelism in our code, right? So again, yeah, the reason it's different is because we can't interleave these instructions in the middle in any way we want, right? Because yes, there is a store here, but then the modify and the write is done to a thread local register. So it doesn't, like the fact that we've preempted it doesn't matter because the state is only in one thread, right? Each thread has its own copy of this, or that's what's different. So anyway, looking forward to what's going to happen next week. Parallel programming topics. We're going to talk a lot more about what lockings are, what a deadlock is, like data races, all of the normal stuff that you'll want whenever any interviewer asks you about parallel programming questions. Right. So that does it for the main part of the workshop.